Welcome back, everybody. Today, we're going to be continuing our discussion about quantum phase estimation, and in particular, I'm going to be showing you a particular application of quantum phase estimation known as amplitude estimation, which combines ideas from amplitude amplification and phase estimation. So let's jump over and start the math. Okay, so to begin with, let's just add a new section. Here we go. Okay, so to begin with, last time what we talked about is we talked about the quantum Fourier transform, and in particular, we showed how that can be used in order to implement a technique known as phase estimation. And the way phase estimation ended up working is, let's assume that we have a state U acting on a state that I'll call psi sub p. Now, psi sub p is an eigenvector of U, meaning that the action of U on this just multiplies psi p by a scalar. Specifically, it multiplies it by e to the 2 pi I. What did I ended up calling it? Yeah, I was calling it q sub p over here divided by 2 to the n psi p, where q sub p is in 0, 2 to the n. And in this context, q sub p is a real number. However, the simplest cases for considering phase estimation are the case where q sub p is in z, right? So if we have an integer, then actually it turns out quantum phase estimation, as we showed last time, leads to no error. But the process for quantum phase estimation is pretty simple. How it ended up working was the following. We add this over here and our quantum state, psi p, being fed into the bottom. And then what we did is we had a series of controlled unitary evolutions. Going all the way down to u 2 to the n minus 1. Now, once we've done all of this, then what we need to do is we need to take the inverse quantum Fourier transform on this side, and the result over here will be approximately equal to this value of q sub p. Now, just to show you how this all works, let's look at this in the case where q sub p is an integer. If q sub p was an integer, then what the circuit will end up doing is it'll take 0 tensor n over here, and the Hadamards will map this to 1 over root 2 to the n, sum over j. And if you're confused about that step, take a look at some of the previous discussion of the quantum Fourier transform about why that's true. But it's just a direct consequence of the fact that Hadamard acting on 0 creates a uniform superposition. Okay, so Hadamard tensor n acting on 0 ends up giving us now the sequence of controlled unitaries by the definition of what the unitary does, which is here. We end up getting that this will give us sum over j e to the 2 pi I j q sub p over 2 to the n. The reason why, again, is that we can see that if this over here is representing j1 through j2 all the way down through jn, we can see that this is building up a binary expansion of u to the j applied down here. And the action of u to the j acting on psi sub p is just this guy over here. Oh, but I have to include the psi sub p. So there we have it. This is the action of the state. Now here, we're going to do one of the things that is actually kind of one of the most powerful things of quantum computing, but yet it looks really stupid when we write it this way. But it turns out that this is actually incredibly powerful. People come up with a name for this effect. They call it the phase kickback effect, but it's not really even an effect. It's just noticing that we can write this phase anywhere we feel like in the vector because it's just a number. So I can write this actually as e to the 2 pi I j q sub p divided by 2 to the n j psi p. Further, I can put brackets anywhere I feel like. So I'm going to choose to put my brackets here and here. Okay, great. So nothing really has happened, but something kind of has. Recall that the definition of the quantum Fourier transform acting on an integer q sub p is actually equal to 1 over root 2 to the n sum over j e to the 2 pi I j q sub p over 2 to the n j. So therefore, these two are exactly the same. So this whole circuit is equal to quantum Fourier transform acting on QP tensor psi sub p. Okay, and now if the last step of the algorithm involves applying the inverse quantum Fourier transform, which will kill the quantum Fourier transform and will just give us QP psi p. So even without measuring, what phase estimation will end up doing is it'll end up getting this integer QP, which specifies uniquely this phase. And in particular, once we have the phase, if we learn what QP is, given we know what n is, then we know that the eigenvalue can just be computed as e to the 2 pi I q sub p divided by 2 to the n. So learning q sub p is equivalent to learning QP. Okay, now, so that's how this process ends up working. Let's take a look at then a more complicated example where we're also dealing with the assumption that q sub p is an integer for simplicity. If q sub p is not an integer, then the state that we'll get over here will not be precisely the quantum Fourier transform of one of these values. It'll be approximately the quantum Fourier transform. And so what we need to be able to do is we'll need to be able to deal with the error analysis in that particular case. And fortunately, we've done that error analysis already, so we can kind of bootstrap off of it. But for the moment, let's actually consider the case where we have a superposition of eigenvectors. So fun fact, every Hermitian or unitary matrix has a complete set of eigenvectors. This implies that the eigenvectors can be used as a basis. So what this ends up meaning is that any state psi over here can be written in the following form: sum over p, c sub p, psi p. Okay, where all the psi p's can be chosen to be orthonormal. Now, furthermore, we have that the unitary matrix acting on psi sub p, just as we defined before, we're going to take to be e to the 2 pi I q sub p divided by 2 to the n psi p. All right, fantastic. So now, what happens when we apply phase estimation to psi? Well, phase estimation over here is just the circuit over here. It doesn't even necessarily require measurement. So this is unitary, and therefore it is a linear transformation. And because it's a linear transformation, we can end up writing it as follows. We can write it as a sum over p, cp, pe, psi p. Now we just argued what the action of PE psi p is. PE psi p, I guess I should put a 0 acting on here in order to be able to store all the information. But PE psi p will just give us the value of QP in that register. So this will end up giving us sum over P, CP, QP, psi p. Okay, and so that is the action of phase estimation. So what happens when we measure if we measure Q sub P, then basically what we end up doing is we end up projecting our state sum over P, CP, QP, psi P to QP psi P with probability. Well, let's just write this out. This is phi, right? So the formal way that we would write that is we would write this as the expectation value of a projector onto this particular value. And that projector, since we're measuring, we want to figure out the probability of measuring QP, that projector is just going to be Q sub P here, Q sub P, and we don't care about the state, so we put an identity in here. And so this is the indicator function that counts all of the states whose probabilities we want to estimate. And therefore, this is just equal to, unsurprisingly, CP squared when we go through and do the inner products. So the probability is just the square of this. So you'll note that by measuring Q sub P, we do actually do something really kind of cool. What we're doing is we're measuring actually equivalently in the eigen basis of the unitary U. So with probability CP squared, we are going to project onto one of the eigenvectors down here. So this process actually projects onto eigenvector psi p and gives eigenvalue Q sub p. Now, of course, there's a caveat to this, because what if we have that Q sub p is actually equal to Q sub p prime, where P is not equal to P prime, i.e., what happens if there's two different vectors that happen to have the same eigenvalue? Now, people will refer to this in physics as being a degenerate problem. But the basic idea is if we have that case, then if we go through and perform our projectors, what we will end up getting is we'll end up getting that this is actually equal to, well, there's going to be two states that actually will have this projector. So we'll have our state be of the form QP psi p CP star, and I'm just doing the two-dimensional subspace over here where we have two different values, for example, that evaluate to the same value of QP. So if we just consider that, then we have this over here, QP. Sorry, it's both QP over here. And then we are going to have psi p prime, though. Different state, but same value. Okay, and then this is Q sub P, Q sub P, tensor identity, all multiplied through by the exact same thing we have above, but the other way around. plus Q sub P psi P prime CP prime. Okay, and this, when we multiply through and use the orthogonality properties of psi P and psi P prime, because these two are orthogonal to each other, this is actually just equal to absolute value of CP squared plus absolute value of C prime, CP prime squared. Okay, so this we can think of as the probability of P plus the probability of P prime. So if we end up with a situation where we can't distinguish, or it turns out if it's impractical to distinguish between the two values, then the resulting quantum state that we will end up getting out will actually be a superposition of the two eigenvalues. So this measurement, while it does a measurement in this basis, we're not guaranteed what linear combination of the two vectors we're going to project into if they have the same value of Q sub P. Okay, and so that is that's the only caveat that I wanted to mention. But apart from that, this really does give you a fantastic way of projecting yourself onto the eigenbasis of a particular unitary transformation. Okay, fantastic. Now, let me talk about the last case that I wanted to do for this. And so if you understand anything about this, understanding the argument up through this point, this is essential. This part over here is icing on the cake of just to understand what happens in the case where Q sub P is not in Z. Okay, and so we mentioned in this particular case, what ends up happening is we end up having that the success probability isn't 100% in this particular case. Basically, what we ended up showing last time is that the probability of success, if we want to shoot for a probability of success, equals 1 minus delta, and we want the accuracy when we succeed equals, or the error when we succeed to be equal to epsilon, then the value of n that we need to take ends up scaling like n equals ceiling log base 2 of pi over epsilon plus ceiling of log base 2 of 2 plus 1 over 2 epsilon. Delta. Okay, so this value of n will suffice in order to be able to hit this. So let me just explain again what these concepts are. This actually is very similar to what's seen in this form of this area of machine learning, if you're familiar with it, called PAC learning, or probably approximately correct. And so basically what this ends up saying over here is that these types of bounds say that, okay, with probability over all the samples that we take, some fraction 1 minus delta will be good. And when good, error is less than or equal to epsilon. When bad, then who knows? Things can go, in theory, arbitrarily wrong when we're bad. We could be pi radians off in our estimate of the eigenvalue. However, in the majority of the cases, 1 minus delta will be good. Now, for all practical purposes, what we normally will want to do is we'll want to pick delta to be some value that is less than 1/2. Usually 1/3 is kind of customary. Now, the reason why is that the cost of phase estimation is in order 2 to the n, which means that if we plug all of this in, this is in order 1 over epsilon delta. Okay, so if we want a very small probability of failure using this formula, the cost is enormous. So the right way to deal with this is the optimal way is we pick delta equals 1/3, then then repeat algorithm order log 1 over delta prime, where delta prime is the final error tolerance that we want to hit, or the final probability of failure that we want to hit, and take 1, 2, 3. That we compute the median of the result. Now, for the erroneous cases, in order to dominate the median, then what we need is we would need to have a number of failures okay, let's call this capital K, greater than K over 2. Okay, in order for it to be able to affect the median, because the median, if there's greater than 50% of the data, if it ends up coming from the good cases, then we know that we're going to be worst case scenario epsilon far away, and that's within our error tolerance. But the bad cases might end up dominating. So if the number of failures is greater than K over 2, then that's the situation. But the probability of having greater than K over 2 failures is actually given by the binomial distribution. Basically what this, the binomial probability distribution says is that the probability of K failures. Hey, how's it going?
Hi, sorry, I didn't know you were in there.
Hey, no worries.
I just checked the data drops.
Cool.
Sorry about that.
No problem.
Okay, we come in.
Just give me a sec. I got to stop recording. Okay, never mind. I'm sorry. Let me just stop this recording. All right, never a dull moment. And me being the lazy professor that I am, I've opted to not restart the recording. So apologies for future watchers. So let me go back to sharing my screen. Okay, so now the probability of this is given, by the binomial distribution, which is the probability of exactly K failures is going to be, K over 2 failures would just be K choose K over 2 times the probability of failing, which is 1/3 to the K over 2, and then 2/3 to the K over 2. And you can see that these are very small numbers, and probability of failure, when we sum up all the rest of these values in the binomial distribution, we expect to see something that is exponentially decreasing. In fact, we can use a Chernoff bound to rigorously end up bounding the area under this curve. And what we end up finding when we end up doing this is that the Chernoff bound says that the probability of doing this ends up scaling exponentially with K. All right, and so then by going through and figuring this out, you can see that if we wanted to make the probability of failure delta, we only need to choose a K to end up going like log 1 over delta. So That's where this part ends up coming in. It's from the Chernoff bound, which ends up giving us that the tail probability for the binomial distribution shrinks exponentially. So this ends up implying, once we do that, that the probability of getting a final failure goes like log 1 over delta divided by epsilon. Okay, cool. So that's how you would actually do it in practice. But for a single run, this is kind of the best formula for us to work with. All right, wonderful. So now let's just work with that original formula and acknowledge the fact that we're going to choose delta probably to be something modestly large, but epsilon will probably be pretty small because we're just going to be using our phase estimation algorithm in like steps 1 and 2 over here when we're repeating the phase estimation algorithm a relatively large number of times. Okay, so that's what we're going to be doing. Now, if we have the case where let's consider, all right, our initial case where we apply phase estimation on our state psi, which I'm going to assume is just like before, sum over p, CP 0, put a 0 here, and psi p. Okay, now this is just going to give me sum over p, CP, inverse QFT acting on, this is going to be 1 over root 2 to the n, sum over j, e to the 2 pi I q sub p divided by 2 to the n, j, I need to put a j up here, and the psi sub p. Okay, so just like before, if we measured this, then life would be, if q sub p was an integer for all p, then life would be good. But now it's not, and so these two are not Fourier duals of each other. So we can't like invert the Fourier transform and get back precisely an integer. Instead, we're going to have, if we apply this with the value of n that satisfies this bound, then we're going to have a state that is going to be of the following form. I'm going to express it as follows. Our state is going to be equal to the sum over p, c sub p, times the fraction of the quantum amplitude that succeeds. So these are going to be the values of q such that the phases that we've inferred satisfy q minus q sub p times 2 pi over 2 to the n are less than or equal to epsilon. And this over here I'll refer to as the set called good. And I'll refer to these coefficients that we end up getting for the expansion of the state a sub q and psi sub p over here plus sum over q such that, you guessed it, it's the other way around, q minus q sub p. Oh, sorry, this should be absolute value here, such that q sub p dot 2 pi over 2 to the n is greater than epsilon. And I'll call these coefficients bq, q psi p, where, and this state will be bad, or this set will be bad. Now here, we're going to assume then that the sum over good of a sub q squared, because we know that the probability from our previous analysis, the probability of failure or success is greater than or equal to 1 minus delta, then these coefficients, whatever they are greater than or equal to 1 minus delta. Okay, and similarly, the bad probabilities, absolute value bq squared is going to be less than or equal to delta. All right, fantastic. So this is the this is actually all we really need to know for this. Now let's actually go and take a look at what the probability of measuring a particular value of q prime. So in particular, just to give some intuition about this, let's imagine that we measure q and get q prime sub j, where q prime sub j minus q sub p times 2 pi over 2 to the n is less than epsilon in absolute value, i.e. q prime j is good. All right, so we've got a success. And further, assume that a q prime j minus q p prime times 2 pi over 2 to the n is greater than epsilon for all p not equal to j. Okay. Or I guess I mean that for all other integers p prime, that basically that this outcome will be in the bad set. When we go through and compute the probability from this, we end up finding that the probability is basically going to be the probability from the first term, which is the absolute value of c sub j squared times the coefficient that we end up getting from the expansion, which I think I called it aqj prime. That's kind of weird. Okay, but whatever. Times the probability that, and then the probability that we end up getting it from the other state is going to be plus order delta. Okay, so this will be the probability of us getting it. And this is here just the prob of measuring the state with the value, I guess, j. Now this will be the coefficient corresponding for the particular error. And this is a negligible failure probability. Okay, so with high probability in this particular case, what we do is we project ourselves down into a single vector. Okay, and the thing that's worth noting is that no matter what we do, when we perform this transformation, we'll kind of map ourselves, if we do this, to a state that's going to be approximately Cj a q prime j q prime j psi j plus some error, and put a normalization constant over here, beta, where beta is in order delta. Actually, technically, I guess root delta. So this is going divided by, I guess, some normalization constant, which would be c sub j absolute value squared a q prime j absolute value squared time plus order delta. All right, So this is our expression. And the key thing to note is that apart from this small amplitude over here, corresponding to the remaining states, what ends up happening is that we end up primarily getting, after a single measurement, our state being concentrated on the state psi j. But the state psi j is still there. So what we can do is we can keep applying PE. Now, when we do this, with ever increasing probability, as we get more and more data, what will end up happening is that the data, where did my writing go? As we collect more and more data, then we will project ourselves or a single eigenvector. Because what we'll have is we'll have some small probability like order delta or small amplitude order delta on these erroneous states and order 1 amplitude here. And every time we apply this reprojection, where we keep on doing this because we still have our quantum state here, so we can keep applying phase estimation to our heart's content. So if we kept on doing this, then we can actually exponentially increase our confidence that our state is actually legitimately real. And so that's basically how we go about doing this. We keep the state and repeat order log 1 over delta times. And then from the exact same Chernoff bound style argument, you can reason that with extremely high probability, the state that you end up getting will actually have projected yourself onto one of the eigenvectors, which is awesome. So that's how this whole procedure works. The key message is that everything is still perfectly fine when you apply phase estimation and you apply it to a superposition of quantum states. Or also, it's also fine when you don't end up having a precise eigenvectors. It's just that you need to acknowledge the fact that there's going to be some non-zero failure probability if you don't have your eigenvalues being integer multiples of 2 pi over 2 to the n. Okay, so that's phase estimation in a nutshell, and the TLDR is that basically what happens, what phase estimation kind of does, is it will end up mapping your state 0 phi p over here to a state that is going to be of the form sum over j a j e j psi p plus sum over j in good in bad aj ej psi p. Okay, and then basically what you can do is you can just measure and repeat this process, and it will project yourself onto an individual eigenvector. But everything works exactly the same. So the real question now is, how do we apply this? Now, the way that the easiest application for all of this, and arguably the most useful one, is amplitude estimation. Now, the idea of estimation ends up is a quantum analog of the following classical statistics problem. And this kind of classic statistics problem that we end up taking a look at is estimating the bias of a weighted coin. Okay, so for the problem of a weighted coin, imagine what you have is you have, some coin over here, right? And, you ordinarily it would end up looking like this, but you might have somebody who, sprinkles some like magic fairy dust on the bottom of this and ends up dramatically increasing the mass of one of these two sides, making it more likely that the coin, when flipped, will end up going face down rather than face up. So we'd like to be able to estimate this. And the way that basically you end up estimating this is what you do is you flip. The optimal algorithm for doing this is we flip the coin a bunch, compute the number A equals the number of heads divided by the flips, and return 1/2 minus A as estimate of bias. Now, the standard deviation in the estimate of the bias that we end up getting this is just the standard deviation of the mean. And so the standard deviation of this estimate is actually just going to be in the number of flips. This implies that the number of flips is in order 1/epsilon², which coincides exactly to kind of the number of measurements that we would need to do to estimate a probability. Because after all, estimating a probability, that's really the exact same problem as estimating the bias of a coin. So we need order 1/epsilon² samples to do it. And we can see actually that this is in fact optimal, that omega 1/epsilon² is also needed classically for this. And the reason why is that you can actually end up using this argument known as the Kramer-Rao bound, which is a fantastic way of proving lower bound on the variance of any unbiased estimator of a quantity. Okay. Wow, today is just full of technical fun. All right. So Kramer-Rao bound ends up giving us that actually this is optimal. However, amplitude estimation allows us to solve the problem using order log 1/delta divided by epsilon quantum samples. Okay, cool. So that's a quadratic gap between what we can do quantumly and the best that we could possibly do classically. And this is actually the root of speed ups in areas such as machine learning and other areas. So how does amplitude estimation work? Well, the way that amplitude estimation works is it actually combines two ideas that we've already seen. Amplitude estimation, it combines amplitude amplification and phase estimation. Now, it's been a while since we've talked about amplitude amplification. So you might wonder, well, what's the link with amplitude amplification? Well, the key idea behind amplitude amplification, if you recall, is let's draw out the circle over here. And we've got two vectors. We've got a vector, which is a projection onto the good state of our initial state, psi, going up here. And we've got our vector, psi, over here. Okay, so, or I should say, this vector is PG psi divided by the length of PG psi. Now, if you recall that we had a walk operator that we use in amplitude amplification, which was defined as negative the reflection about the good state, which we can write as that. Sorry, got the order backwards. It is negative identity minus twice the reflection about the initial state times the identity minus twice the projector onto the good space. And if you recall that the what this ended up doing, if this angle down here is theta, where theta is equal to the arc sine of the square root of the probability of good, as in this case, it is the probability of good is just actually psi PG psi. Okay, so if this is some probability of getting a good outcome, then theta is defined to be the arc sine of the square root of that probability. And further, we can end up seeing that this first reflection, of course, gives us an angle theta reflected about the axis orthogonal to PG, and then reflecting about psi ends up rotating us up an angle now of 2 theta over here. So the net that we end up seeing is we started here and we ended up there. The net is a rotation that increments us up by 2 theta. So inside the span of psi and the walk operator acting on psi are the matrix that describes this rotation in the 2-dimensional space that we're interested in is W. I'll write this as a block matrix that is specifically inside this space spanned by W and W psi. This is actually equal to cosine theta, sine theta minus sine theta cosine theta. Actually, I think I mean 2 theta over here. Wonderful. So this is our walk operator. And this is actually equivalent to applying a y rotation through an angle, annoyingly, of 4 theta inside the subspace psi walk psi. Okay, cool. So the eigenvalues of Ry actually are pretty easy to figure out because Ry is actually equal to S H R Z H S stagger. I might have gotten the S and the S staggers backwards, but it still ends up actually showing you that the eigenvalues of this are actually the same as this, and RZ is equal to e to the negative theta over 2 I 0 0 e to the I theta over 2. So therefore, the eigenvalues of Ry of 4 theta are, just by taking a look at this, because the eigenvalues of a matrix are defined to be the values that we end up getting after applying a diagonalizing transformation. These operations inside this 2-dimensional space end up diagonalizing it. So therefore, the eigenvalues of this are equal to e to the plus minus I 2 theta in this context. Okay, fantastic. So why is this important? Well, again, this is important because these are equal to e to the plus minus I twice the expectation value of PG psi, twice the arc sine of the square root of psi PG psi. Okay, so basically from this, we can actually figure out what the probability of getting a good state is, because that's directly related to phi. Now, or theta. Now, if we had a way of estimating the phases of eigenphases of a unitary matrix, then we could end up backtracking this. So let's just assume, for the sake of simplicity, that that 2 arc sine square root of psi pg psi. Let's assume that this is equal to 2 pi q divided by 2 to the n. All right. And so what this ends up meaning is that basically we can end up, if this approximation is true, and we're just taking this just to be able to understand more simply how this exactly is going to work, then we can apply phase estimation to unambiguously learn one of these two eigenvalues, either the positive or the negative. So our quantum state, if we end up preparing our state in this particular form, we're going to have a state, our state psi. It's going to be equal to A1 psi plus A2 psi minus over here is equal to e to the I to arc sine of psi, and u acting on psi minus is equal to e to the negative to psi pg psi. All right. Now, again, we can always do this because of the fact that the eigen vectors of a unitary matrix form an orthonormal basis. And so I'm just expanding this inside the two eigenvectors that inside this two-dimensional subspace of interest. There are other eigenvectors, obviously, but all of these are orthogonal to psi. So for our purposes, we really don't care about it. We can only focus our attention on this two-dimensional subspace, which is the only important part for the problem. So, okay, these are the particular eigenvalues. And so we can use our results that we ended up having before. So PE acting on psi will give us one of two results. This will end up giving us A1. Now this the positive branch will give me 2 pi, will give us a value of q and psi plus with it. Now the negative branch will give me A2. Now we need to correspond to this will correspond to the negative phase for this. Because it's negative phase, it's got a difference of pi. And so this will give me q plus 2 to the n minus 1. Because if I put in 2 pi times 2 to the n minus 1 divided by 2 to the n, this is just equal to 2 pi over 2, which is pi. And that corresponds to e to the I pi equals -1. So this corresponds to the negative solution. So we're going to have these two values as our only two possible eigenvalues. So let's measure. So if we measure and get a value that is q prime, if q prime is greater than 2 to the n minus 1, then that will correspond to this negative branch. And so then what we're going to do is we're just going to subtract pi off of it. And so then we'll take q prime goes to q minus 2 to the n minus 1. And that will give us our corresponding value of q from this branch over here. Okay. Q prime. Okay, so that's our first step. Next, what we do is we let we want to work back in order to be able to figure out what this guy is. So in order for us to be able to figure out this guy from the results of phase estimation, what we end up doing is we need to divide our result by 2. So we need to take first q prime goes to, or let theta hat equal 2 pi q prime divided by 2 to the n. Okay, so now that we've done that, we've converted this over here to an actual phase value. And now that we've converted it to a phase value, we can work backwards. So we end up giving our estimate then for the probability, which is psi pg psi. This is just going to be equal to our estimate for theta hat divided by 2. We'll then need to take the sine of the result, and you're going to need to fix the square. So we square. All right, fantastic. So that ends up giving us our result, and this will allow us to unambiguously compute the probability of this working, given the fact that we assumed that this is an integer. So you can see that what we can do is we can apply phase estimation to estimate the probability using amplitude amplification, not as a technique to be able to boost the probability of success, but a way to interconvert the probability of success into a phase. And then we use phase estimation to convert that phase to an integer. So that's it. We're just using amplitude amplification as a means to transduce between a probability input into a phase input. So another way of thinking about this is that this is a way that we can turn an amplitude oracle into a phase oracle. All right, so that's how this ends up working. Now, the case where Q is not an integer is the last thing that I want to talk about, okay? So in the event that this ends up happening, we can use our results of phase estimation to say PE will yield a value theta hat such that theta hat absolute value will be less than epsilon, less than or equal to epsilon, with probability greater than or equal to 1 minus delta. And our cost of getting this estimate is going to be in order log thing, again, this Chernoff bound argument in order to boost the probability, the scaling from 1 over delta, like we would get with the naive formula, to log 1 over delta using amplification. Okay, so that's the cost of doing that. However, the question is, well, all right, well, how do the errors propagate? We have sine squared theta hat over 2 plus epsilon minus sine over epsilon, theta over 2 is what we kind of want to figure out, right? Like, what's the error in our estimate in the end that we end up getting of our particular values? Now, I can go through some the details for this, but the key thing to end up noting is that this is a Lipschitz continuous function. So because it's Lipschitz continuous, there exists some constant L such that sine squared theta over 2 plus epsilon minus sine squared theta over 2 is less than or equal to L epsilon of Lipschitz continuity. Okay. And so, yeah, because of the fact that it's continuous, and in particular, we can actually say something a little bit stronger because the function is differentiable. It therefore is Lipschitz continuous. So such a constant ends up existing. So if we're just interested in looking at the big O scaling, what this ends up saying is that the worst case scenario that we're going to end up getting with this particular function is that the error that we have in our approximation is going to be some constant factor worse. But big O doesn't care about constants. Epsilon over L is equal to, or shrink our values of epsilon in order by factor of L in our original estimates in order to make sure that the final error is epsilon, but that will only change the cost by a constant factor, which disappears in a big O calculus. So the simplest argument to end up giving you the scaling of the cost is just to invoke the continuity and say that then the final cost of learning the amplitude is order log 1 over delta divided by epsilon. Okay. And so that is how amplitude estimation ends up working in a nutshell. And again, it's an invaluable technique that ends up getting used over and over again in order to be able to estimate probabilities, as well as giving us a way of estimating overlaps and other related quantities. So it's an absolutely vital technique. But thanks a lot. I hope you enjoyed it. And next time we're going to be looking at further ways that we can end up using phase estimation. And in particular, we're going to be covering a different approach known as qubitization. Thanks a lot. I'll see you next time, and hopefully less surprises next time.